Hello everyone, thanks for joining this presentation on Hector. My name is Xu Ruifan. I'm a PhD student at Peking University. Today, I'm going to introduce Hector, the multi-level paradigm in hardware synthesis. Hardware synthesis technique adopts a higher abstraction to improve the productivity of hardware design. Hardware generator often focus on a specific domain and generate hardware with domain-specific optimizations. High-level synthesis automatically generates hardware from a behavioral description written in high-level languages such as C++ and OpenCL. Hardware generator makes use of domain knowledge to improve productivity. These generators often focus on a specific domain such as tensor algebra, streaming, and spatial accelerators. High-level synthesis automatically converts high-level description to RTL design through allocation, scheduling, and binding processes. These tools are often implemented on existing software infrastructure like LLVM. Both synthesis flows require substantial engineering efforts due to RTL's weak expressivity and low level of abstraction. However, these different methodologies share some similarities in the intermediate representations, such as all of these is the hardware generation from a high-level abstraction, and they also have some common hardware control logic. Here we propose Hector, a two-level IR providing a uniform description for different hardware synthesis methodologies, which provides enough expressivity and flexibility. The two-level IR and all the transformations are built on the MIR infrastructure, which further improve the reusable of this framework. The IRs in Hector are converted to synthesizable RTL programs through a series of transformations, and the unified IR for different synthesis approaches makes it easy to design new hardware synthesis techniques and explore different methodologies. Here, we use Hector to build a HRS tool. Hector can flexibly support different scheduling strategies. Polyguest is used as Hector's front-end to convert C programs in SCF dialect in the MIR. To build a complete HRS flow, we additionally implement an SDC-based modular scheduling that converts SCF dialect to the TOIR. The scheduling results can be easily represented by TOIR because of the concise structure of the time graph. Hybrid scheduling can be easily obtained by converting the minors of certain edges from static to dynamic. This demonstrates the Hector's expressivity and flexibility. The multi-level paradigm also provides the ability to design hardware at various levels. It enables that a single PE can be configured at multiple levels, including TOIR and HEC-IR. For the PE with simple behavior, SCF dialect can be automatically lowered using the HRS approach described before. The interconnection is configured in HEC-IR. A six-topic array generator is easily achieved by generating Hector IR, which reduces redundant implementation. With the development of hardware design, hardware verification is still a big challenge. Existing verification approaches still stuck in scalability and human efforts, which cannot catch up the development of hardware synthesis. However, it's still an open problem on how to improve the scalability of verification. Here, a suitable IR with the multi-level paradigm like Hector can bridge the semantic gap between high-level abstraction and RTL implementation. It's much easier to store necessary information in the synthesis flow and can avoid extra analysis from the RTL programs. Verification in the intermediate abstraction further improves the reliability and transparency of the synthesis flow. HRS as an example. Existing HRS tools only provide software level and RTL simulation, both of which have many shortcuts. Software simulation ignores the hardware structure and cycle information, while RTL simulation has a low level of abstraction and is very time-consuming. The semantic gaps between software and RTL may lead to a mismatch. there are many reasons leading to the C simulation and RTL simulation mismatching. Software simulation can be incorrect due to ignore the transformation annotated by the pragmas and also ignore the hardware information like dynamic behaviors. And what's worse, the mismatch may be triggered by the HOS tool bugs. This problem can be partially solved by a cross-level debugger. The multi-level paradigm enables a cross-level debugger for the hardware synthesis. Besides software simulation in the instruction order, the TOR can be regarded as a time graph with computations on the time edge. The Hector is much closer to the hardware with the explicit definition of the compute units and registers. The TOR is suitable for data flow information, while the Hector is suitable for the low level of abstraction like handshake protocol or the register sharing. The equivalence mapping in the synthesis procedure can also be easily obtained, which must be obeyed during the cross-level debugging. The high-level IR is simulated as the traversal on the time graph, while the low-level IR is more likely to a state transition between different states. This debugger further improves the reliability and the transparency of the synthesis tools. Conclusion: we address the benefits of multi-level paradigm. It provides a promising way to build a new synthesis tool with human efforts, and it also enables cross-level debugging in the intermediate abstraction. After all, verification for hardware synthesis remains a challenge, and an automatic verification approach with few human efforts is necessary. Thanks for listening.